Mhm. Good evening and welcome to the third installment of Adventures in Particle Physics, coming to you live from the University of Stavanger in Norway. My name is Alexander Rotkopf. I'm a physicist here at the University of Stavanger, and I will be your host for this evening. This week, the Institute of Mathematics and Physics at the University of Stavanger is hosting a virtual physics conference with more than 300 participants and more than 150 presentations of new scientific findings in fundamental experimental and theoretical physics. This research is made possible thanks to your taxes, and we are aware of the responsibility that comes with your trust. As scientists and teachers, we wish to share with you what kind of physics topics are discussed at this conference. And to do so, we've prepared 3 inspiring presentations for you this week. 2 already took place, one on Monday, one on Wednesday, and the third one is today. The speakers are all physicists who would like to share with you some of their insights and fascination for studying the microscopic building blocks of our universe and the forces that tie them together. If you have questions or comments during the presentation, feel free to leave them in the live chat window right next to this YouTube video. I will be collecting your questions and comments, and together with the speaker, we will get back to you at the end of the presentation. So stay tuned until the end for a live question and answer session. The video that you're watching is a 360-degree virtual reality video, and you can adjust its orientation and viewpoint by clicking and dragging the video on your screen. Note also that the materials for today's presentation you can find in a link in the description of the video. Our speaker tonight, Zhongbo, is an associate professor and group leader at the University of California, Los Angeles. Zhongbo supervises a research team that works on uncovering the secrets behind the strongest force in nature, the aptly named strong force. And his group uses advanced mathematical tools to, for example, better understand the 3-dimensional structure of the inside of the proton, which then helps the community to, for example, interpret experimental results from collider experiments at the CERN laboratory in Switzerland. And as it's customary for successful physicists, Zhongbo, during his career, has already worked at several different international institutions, for example, the Los Alamos National Laboratory in the United States or the Brookhaven National Laboratory in the United States, before joining the University of California. And tonight, Zhongbo is taking us on a journey of how physicists discovered and then explored the strongest of nature's forces. So, Zhongbo, please, the virtual stage is yours.
Yeah, thanks a lot for the kind introduction. So I'm very happy to be here, even though it's virtually. So thanks for the kind invitation. So today I want to share with you like strong force. In particular, I want to share with you the journey where physicists explore the structure of matter, starting from the rules of the experiment to the currently research frontier called the electron-ion collider, which is going to be built by around 2030. I'm a faculty member from UCLA. So if you are interested about our scientific opinions, you can also follow us on Twitter. So the understanding the structure of matter is really coming from our curiosity, because we are really interested in the questions such as what are we made of, like the universe, the stars, our human itself, and all the substance around us, how and what are these things are made of. So these questions are being asked for thousands of years ago, but the only really scientific contributions coming in through only around 18th century. So these days, this is our current knowledge of the structure of matter. So for all the matter, such as a leaf, is made of molecules, and molecules further made by atoms. So the molecular atoms, these guys has a typical size 10 to minus 10 meters, which is a really small number. Right? And then if you further look at the atoms, you will find out outside of the atom, those are the electrons, which is negative charge. Inside the electron, there's a core, what we call atomic nucleus. So this core is much, much smaller than atom size itself. It goes like 10 to the minus 14 meters. So in a sense, it's 4 orders of magnitude smaller in terms compared to the atom size. If you go further about atomic nucleus, and we'll find the positive charged protons, and then the electric neutral neutrons. Okay? And each of them has a similar size, is something like 10 to the minus 15 meters. This is what we call 1 Fermi. Okay? A Fermi, it means femtometer, 1 Fermi. It's 10 to the minus 15 meters. You can go further. These proton neutrons also have a fundamental structure. The fundamental structure are composed by quarks. Okay, quarks, for example, like protons composed by 2 up quark, 1 down quark, and neutrons and 2 down quark, 1 up quarks. Okay, and up to that point, that's it. That's basically those quarks are the fundamental particles in our current knowledge. Those quarks, they are grouped together. So by those curly yellow bluish like a spring, those yellow spring is what we call a gluon because they glue quarks together. Okay? They glue quarks together through the strong force. Okay, so this is our currently structure of matter, current understanding. So today, our lecture is going to try to tell you the history, how we ended up with studying from very beginning until the most recent in the structure and how we're moving forward continuously. The 4 fundamental forces we already know. That's gravity, which is responsible for how all those planets are circling or orbiting around our sun. There's electromagnetic force. So for example, shown over here is actually the electric light rain in Los Angeles happened about 2 years ago in 2019. That's strong force. So strong force, as we just said, strong force is the strongest force in nature who is responsible holding all the protons and neutrons together. Okay. They are so stronger, they have to be stronger than like electric force between those positive charged protons. Otherwise, they will fall apart. Right? So strong force is so strong, they're holding them together. There's a last force is called a weak force, which we will not discuss much today. It's basically responsible for nucleus decay. So for example, over here, this is called a beta decay, which in this case, you converted one of the proton into a neutron. So we're going to mainly concentrate on how the strong force and affect our theory and our structure of matter. So I think that's, yes, so the structure of matter, as I said, is these questions being asked more than several thousand years ago. But the real scientific development is coming from the 18th century by Darwin. So Darwin developed so-called atomic theory. So in his theory, he assumed all the matters are made of extremely small particles called atoms. So after this one, people made a lot of progress. But the next major discovery to go one step further is really taking more than 100 years ago. So go up to 1911 by Sir Rutherford, which discovered atomic nucleus, that's core in the center of atoms. Okay, you can watch this interesting YouTube video.
In 1910, Rutherford and his co-workers were studying the angles at which alpha particles were scattered as they passed through a thin gold foil. Most of the alpha particles passed through undeflected. However, a few were found to be scattered at large angles, some even back in the direction from which they had come. This meant that they had collided with an object much more massive than the alpha particles themselves, yet so small that only a few alpha particles encountered them. This atomic level view shows what is happening. Most of the atom is occupied by the low mass electrons. The nucleus is small and massive. When an alpha particle encounters a nucleus, it is scattered at a large angle.
So this is exactly through this experiment, and Rousseau find it out. And if you have, so this inside this atoms in the center, there will be atomic nucleus. This is how he came out with his atomic nucleus model. In the center, those are the, very small, very small. All the mass are concentrated in this small volume, and then all the electrons are secondary one. So, and these days, as I said, I'm following Twitter, so I find it out from one of the physicists of Twitter, and you can find this very interesting picture, which is a statue from Shanghai, China. This was exactly Rutherford, and this is his atomic nucleus model. So this is atoms, and in the center, which is really tiny in the center, you see this atomic nucleus. As I said, if you imagine the size of these things, the center of atomic nucleus is 4 orders of magnitude smaller than the atoms itself. Now, after that, Rutherford continued doing performing his experiments, right? So as we said, so when he discovered atomic nucleus, he used an alpha particle to collide with a heavy nucleus. That's how he realized inside there's a small, in the atom, there's a small heavy nucleus. But he started to perform the similar experiments. This time he used an alpha particle to collide with a smaller nucleus. It's called nitrogen atom. So this time, when you find it out outside, okay, after the collision, the 2 particles come out. One is oxygen atom, and the other one is hydrogen atom. You'll find that so hydrogen atom back in that time is the smallest nucleus. So by this experiment, he realized, or he concluded, the hydrogen atom or hydrogen nucleus must to be a part of the nitrogen. Okay, so this is how we discovered the proton. Okay, hydrogen nucleus is really just made by one single proton. Okay, so Rutherford is experimentalist originally from New Zealand. So New Zealand, this is one of the poster stamps memorizing his contributions. This is exactly this reaction they developed. Alpha particle collided with nitrogen to produce oxygen, and then with a hydrogen nucleus. Right. So 100 years later, in 2019, Søren Curie actually made a story and described this whole history how they discovered the proton. Okay, this is his second major discovery in his career life. I find it out reading this story is very nice. This is 2019, May 8th. Okay. By the way, if you wanted to order Søren Curie, everyone can order it, and you can also read it online. It's free. Okay. One of the sentences from reading this is very interesting to read. He said, according to here, it says, in his earlier days, Ansel Rutherford was the right person in the right place at the right time. So this is according to our life experience, right? We find it out. Being the right person in the right place at the right time, doing the right thing is such an important thing. Yeah, everyone knows about that. So I think this is a very interesting article. Everyone should read. After that, after finding a proton, and then people find it out the charge seems not consistent with the mass of the nucleus. So for example, if you're counting all the protons inside the nucleus, and it doesn't make up the entire nuclear mass, it's only making about half of nuclear mass. That same suggests inside the nucleus, there's other particles which is not charged. It's very likely electric neutral particles inside. So, but people didn't know, didn't manage to leave them out. So eventually in 1932, Chadwick and managed to leave this particle out. So Chadwick was a student of Rutherford. He continued doing this experiment using alpha particle to collide with another small nucleus called a beryllium. Right? And after that, this collision, you find that there will be carbon come out, And then there's another particle naturally come out, and it's electric neutral. At the very beginning, people even think about this is probably just a photon, okay? But by measuring the mass and everything, and eventually people figure out it's another particle. It's exactly neutron, and as they propose, so they call it neutron. Okay? Means it's an electric neutral particle, and it's kind of like a proton, except it's electric neutral. After this, and then everything makes sense. The mass of the proton and the mass of the neutron, we add them together, roughly give you the mass of the nucleus. But then there's an interesting problem come out, because immediately realize that all the protons are positively charged. We know positively charged particle that if you compare the force, electric force between them, they repel each other, right? While on the other hand, neutron carries no charge, so there's no electric force between them. Then, because of that, because this repelling electric force, then seems this nucleus cannot be stable. But however, they are very stable, right? So what is exactly the mechanism responsible for holding these particles together? So this is at that time, this when people propose there must be a new force. This new force has to be stronger than electric force and then holding proton neutrons together. So this is what we call the strong force, which is the force responsible for binding protons and neutrons together inside the nucleus. It's so strong, much stronger than electric force. So if you're using like strength, if you normalize the strong force, the strength is number one at order one, and then the electric force is going to be 2 order of magnitude smaller than strong force. Okay, that's why the strong force can very easily hold the protons and neutrons together and without much trouble from electric force. Okay, because the electric force is much smaller. So this number is 1 divided by 137. Its numbers typically work for the fine structure constant. If you further compare the weak force, you'll find the weak force is 6 order magnitude smaller than strong force. If you compare gravity, it's 40 order magnitude smaller than strong force. So far, in terms of fundamental force, strong force is the strongest force in nature we discovered so far. Right? After that, right? After that, what do you do? So you already find that inside a nucleus, you have a protons, you have a neutrons, and you discover them. Okay, so the next thing, what you naturally think about, as a physicist, you think about to do, it will be you want to measure the property or study the property of those new particles. So what kind of property you should start with? If you study university physics, so I teach university physics at UCLA. This is one of the textbook, very popular textbook we use in US. So this textbook, if you go to the chapter when we're talking about electromagnetism, you will immediately realize inside chapter about 28 or 29, it's starting talking about magnetic moment. It basically tells you if you have a spinning charged sphere, and then this spinning charged sphere must have a magnetic moment. In a sense, when you have a sphere which carries positive charge and is starting to spinning this one around, then you will have a magnetic moment. So magnetic moment will lead to an interaction if you put it into a magnetic field. Okay? It's very similar like an electric dipole moment. So in this case, because we have a proton, so I didn't mention the proton is a fermion, it's a spin half particle. Spin half means, so for our purpose, you can think about if a particle has a spin, and then this guy is really spinning around with the center of this particle. So because of that, and by simply just looking at this university textbook, and you realize, okay, I get a spinning charged proton, right? This positive charge is spinning, it must have a magnetic moment. So then you can go further and to see if you perform a measurement, what kind of results you're supposed to get. Back in that time, people already have theoretical studies for electrons. Okay? In particular, so this the magnetic moment for electrons was given by Dirac, okay, by series Dirac. It's also another very well-known series. So he said, electron magnetic moment is simply given by this formula. It's a minus sign because it's electron is negative charge. And with E, which is this is an electric charge. H bar, because this is something related to quantum mechanics. So this H bar is called a Planck constant. It's a fundamental constant in quantum mechanics. And divided by 2 times ME. ME is the mass of the electrons. Right? So this one is already known back in that time. Okay. So then people started saying, so the person who decided to perform this experiment is Otto Stern in 1933. Before he performed his experiments, and he decided to ask around all the theorists' opinion about the proton's magnetic moment. And the theorists, of course, back in that time, and this is the only thing they came out already. So they said, okay, let's make some adjustment from electron dipole, electrons magnetic moment to get a proton's magnetic moment. So how are you going to do it? First of all, the proton is positive charge, right? So you have to convert this minus sign into a plus sign to taking care of that charge. On the other hand, you see they have the same charge. The size of the charge is both are E, right? So that's okay. The other thing you realize, electron and proton, they have a different mass. Okay, in fact, the proton mass is much higher than the electron mass. So you can just replace the electron mass by proton mass, and then you came out with this formula, which you call mu n. So then the series will give back to Stern says, okay, yeah, that's the number you're looking for. You must get this number. So Stern, of course, as the experimentalist, the training for experimentalists is always you don't trust the series so much, right? So you're going to perform, you only believe your own measurement. So he's going to perform his measurement. He's going to verify or disverify and whether this proton magnetic moment is given by the series. Well, it turns out it's not. It's really not. It's completely different. It gives by this formula. It's 2.5. 2.5 is larger than the original theoretical formula, and with some small error bars. Okay. This result eventually ended him a Nobel Prize in 1943. Right? So what is the consequence? What is the implication of this measurement? So then people seriously immediately went back to say what's the implication. Back in that time, electrons, everyone is thinking electron is a fundamental particle. In a sense, it's really a point particle, has no structure. You can think about it's really like dimensionless point particle, has no structure. That's why it comes out with this formula. So if you carry out this assumption to think about if proton is also a point particle, has no charge, no structure, then this is how you can use this formula, directly making some small adjustment. That's how you get this UN. The experimental result came out completely off from your theoretical predictions, pointing out your assumption is wrong. That means the proton cannot be a fundamental point particle. This is the first hint. Proton is not a fundamental particle. It's not a point particle. It's very likely proton has some structure. So since the proton is not a point particle, so they must have some size, right? So then the next immediate question you will ask yourself, so how do we measure the proton size? The performance, the people performing this particular experiment is by Professor Hofstadter, who back at that time was a professor at Stanford. So he decided using an electron to scatter with a proton, okay, such that the hope is by doing these scattering experiments, by measuring the diffraction angle of this electron, they can try to map out the charge distribution of these protons. So so charge distribution is something you measure in a coordinate space, right? In terms of positions, at different places you have a different charge, right? So those are called charge distribution, which is this rho. While in his experiment, he really study like the momentum difference between the incoming electron and outgoing electrons. Okay, so that's why eventually what is really sensitive in his experiments is really some kind of Fourier transform of your charge distribution. This is what we call form factors. Right? So this is the actual experimental setup. Okay, you prepare your electron beam up to this point, you're shooting the electron beam to your proton target, okay, to your proton target, and then you have a detector over here trying to measure how those electrons are diffracted at different angles. This is like Professor Hofstad is actually explained his setup in Blackboard. Right? So now, after that, they came out with experimental data. So this is the cross-section is, in a sense, you can think about it just in a distribution of those scattered electrons, probably as a function of this scattering angle. And then, so those are the data points, as you can see in the middle. Now there's several, so then at this point, you can do several, let me see. Somehow, okay, 1 second. There's some technical issues. It gets stuck. Okay. So at this time, so if you look at this dash curve, dash line, it gives you like how a point charge will come out through these distributions. If you're assuming the proton is a point charge. On the other hand, so it's certainly way off from its completely under the experimental data. On the other hand, you realize, oh, the proton can also have magnetic moment. So you can think about the contribution as point charge. At the same time, there's also point magnetic moment. If you do that, you get that curve which is above that above this experimental data points, that is solid curve above. So it turns out you either overshoot some data or you undershoot some data. None of those theories are correct. So eventually, Hofstad told himself, he said, maybe one of the things he needs to do is to try to figure out maybe the proton has some size. So you're assuming some sort of charge distributions with certain extension of your proton of the charge, okay, within your proton. And then by doing that, by adjusting this size of your charge distribution, you eventually came out with this solid curve, which is exactly fit on top of experimental data. So that parameter he adjusted, which tells you like charge radius of that proton is this number, 0.74 plus or minus 0.24 Fermi. So it's really has some size that close to about like a 1 Fermi. Okay, that's the size and tells you proton really is not a point particle. It really have some size. So these days, people are continue study this type of experiments. So in this Nature article, cover a Nature article, it was produced back in 2010. And then the other one, the next one is the measurement back in 2019. So these days, and people find out the proton's charge radius is something like 0.84 Fermi, okay, which is much more precise compared to like a previous measurement. Now, so you find it out a proton, it's has some size, like close to 1 Fermi. Then the natural question you will ask when you find something at some size, right? Let's say I have a cup has some size. What do you do about it? So like my kids, well, when I show them some box, they will always want you to look at what's inside the box, right? So naturally, exactly the same thing for physicists. I already find a proton has some size, then I naturally really want to know what's inside that proton. So that's exactly these two Parlian theorists, Gell-Mann and Zvi, they performed in 1964. They come out with a model says proton must, inside the proton must have additional fundamental particles. These fundamental particles they called quarks. Right? So for example, if you have a proton or neutron, these are what called a fermion. Fermion means the particles who carries a half integer speed. Right? So in this case, when you have a fermion, you use 3 quarks to form these particles. It's called a baryons. You can also have a pions and a kaons on the bottom side. These two is what we call Mesons meaning it's a boson which carries integer spins. Right? So in this case, they are composed by a quark and an anti-quark. So this model has been very successful, and they are able to use this model to make a prediction for all the mass, even can make even made a prediction for several unobserved particles at that time, and later on all observed in experiments. Right? So it seems it's very natural, right? So this model is so successful, and people starting to believe that's really quark inside a proton. But we haven't seen it. So how are we going to do it? When you believe there's something inside, and then how are you going to convince yourself there's really no stuff inside? Well, if you have a phone and you know that the electronics inside your phone, how are you going to do it? The brute force way is you just smash your phone. Oh, okay. So this one now has a battery now. Sorry for the technical issues. My laser pointer somehow it's auto battery. So now you smash your phone, okay, and then you will say what's inside. Right? That's exactly a physicist is going to do in this case. So I'm going to have an electron. So I'm going to make this electron has a really, really high energy. So I accelerate electron, such that electron has a really high energy, so such that I can heat my proton, which is that yellow blob, my proton really, really hot. It's so hot, the proton will actually broken into pieces. This X was located over that. So it heat is so hot, and it break into many, many pieces. And then I started to measure those pieces, those X. Right? And then from those measurements of the X, I can try to trace back and to figure out what's really inside the proton. This is exactly the theorists and experimentalists working together came out with this model. So it turns out eventually there's really a quarks, which is a charged particle inside the proton. Okay, the electrons really interact with those individual quarks each time. Okay, so this is what we call deep inelastic scattering. Deep means I hit I have my electrons really high energy, so I can hit the proton so hard. Inelastic means I completely break up my proton, okay, and then I measure all outgoing particles. So the three physicists, those three gentlemen who developed these experiments and performed a measurement, eventually come out with this explain all the experiment data. Got a Nobel Prize in '99. Done in a way, of course, the theorist contribution is very crucial. Two theorists, the one Feynman, the other one is Bujorkin, really play a significant role to help experimentalists understand their experiment data, how to present the experiment data such that it's consistent with theorist's expectations. So those are what they call a parton model. Parton is what Feynman called a parton. It's really just a quarks, where gamma and it's a big quark. Okay. Now, after that, the series came around. Okay, so after continuous doing experiments, finally the underlying theory for describing this strong force, for describing the interaction between quarks and gluons came around in 1970s, roughly around 1972. This is called quantum chromodynamics. So, or in short, called QCD. So this theory says each quark, okay, really carries three kinds of charges. Okay, it's just like electric charge for electrons. I have three different kinds of charge. We call it red, green, and blue. Okay, red, green, and blue. If you go to see it over there, so let me see. Yeah, if you see it over here, you can have blue, green, and red. Those are three different types of charges. These three different types of charges, just like electron charges, and responsible for interactions between quarks and gluons. Right? And then this interesting theory eventually comes with further understanding. So these three gentlemen made a further understanding tells us the interactions between those quarks, they actually become weaker if you go to really high energy. Okay, they are very strong if you in the low energy sense, but if you go to really high energy, they are very weak. So this is called asymptotic freedom, meaning so if you remember, if you recall in quantum mechanics, there's an uncertainty principle. If you go to really high energy, that means go to really high momentum. That means in the position space, in the coordinate space, they're very close to each other. So when put quarks very close to each other, and then the interaction is very, very small. Okay? So this is called asymptotic freedom, and then we have another understanding when at this region. On the other hand, if you go to low energy, okay, and then you'll find that the interaction becomes very, very strong. So it's exponentially growing. Okay, so this one, yeah, it's called confinement. In a sense, once you go to range in low energy, all these quarks, they are completely confined inside the proton. They want you to come out, but they cannot. They're really confined. So this is called confinement. So far, nobody has ever seen a free quark coming out. So they are always contained inside the proton. So now this becomes a problem, right? Because we want you probing quarks and gluons, but however, we cannot directly see them. How we're going to actually do it, right? How we actually do it. This is a very important question, and we don't know how to do it yet. Right? So how are we going to, so you, at this point, I want you to make an analogy. You find it out a different branch, different scientific branch. They're actually making a scientific progress by taking a similar approaches. So talking about astronomy over here. So for the astronomy, because we can using our bare eyes to see the stars on the sky and everything, it's very inspirational, right? So that's why we're typically say, look into the skies, improves humanity, right? And then we want you, for particle physics, we want you to say the same thing. So is looking into the atoms. It also improves humanity, right? So in this case, imagine if you, in the astronomy, if you discover something great, let's say if you discover a black hole. Okay? So showing over here, last year, everyone knows the Nobel Prize in physics was awarded to 3 physicists, all related with the discovery of black hole. So shown over here is our colleague from UCLA, Andreas Gates, and then she discovered a black hole in our galaxy. So imagine, let's say, if you discover a black hole, what are you going to do about it? The natural things you're going to do about it is you want you to provide an image of your black hole, first thing. Second thing, by providing that image, you want you to test your theory. In this case, for black hole, describe a black hole, and that's Einstein's general relativity. How are you going to do the image? So the Event Horizon Telescope collaboration performed an image. They captured the first ever image of a black hole in 2019, which is look like this. Right? Yeah, by the way, I want to emphasize this black hole is not the black hole discovered by Andreas Gates. Okay, it's a different black hole. It's not from our galaxy. Now, the next thing is next year they made a further progress in capturing these images. This time, what they do, they perform the evolution of those images over time. Okay, so these are images coming from recording from 2009 up to 2017, close to like a 10-year time, and see how this images actually evolves. This evolution of the image will tell you the dynamics of your black hole, and it can further test the dynamics of your theory. Go even further, this back in just earlier this year, they provide a polarized review of the black hole. So this is the polarized light coming from black hole. So in a sense, you can using on top of your image, you can add an additional twist by doing polarization, or polarization is another word, it's called spin. By adding the spin as a trace, as a tool, you can study the finer structure of your images. This is exactly what physicists, the particle physicists are actually doing these days. We perform an image, we're studying the evolution of image. We're using like a spin as a tool to study like a finer details or correlations of those images. So imaging proton is doing the similar things. Just like an imaging black hole shows the dynamics of gravitational force, imaging proton will provide insights on the strong force. There are many questions you can address by imaging proton. And let me give you one example shown over here. So this is one important question. We wanted to ask, how do the properties of the protons, such as mass, arise from the fundamental quarks and gluons? You might think this is, why do I even ask this question? It feels very naive, right? Because everyone knows mass. So for example, let's say if I bought a bag of 3 oranges, and then I ask you, what is the mass of this bag? You will say, okay, why do you even ask? This is so simple because the total mass of this bag is simply given by the sum of 3 oranges, right? Nobody's going to have any doubts about this statement. That's pretty, common sense. However, if you try to do the same thing for proton, and you find it out, you get completely off. So let's say, as I just said, a proton are composed by 3 quarks, right? And the 2 up quark and 1 down quark. So if I started to measure the weight of those 3 quarks, right, compared to my proton, you're going to find it out. It doesn't contribute that much at all. It turns out the sum of these 3 quarks mass is only counts like 1% of the proton mass. Well, the 90% of the proton mass come from a different place, come from different mechanisms. The question is, where did it come from? Right? So the Einstein already provided an answer for us. Einstein told us, right, E is equal to mc squared. If you invert this equation, you'll get a mass is equal to E divided by c squared. So the energy can convert into mass. So how exactly you do it? It turns out there's a lot of interesting complicated interactions inside the proton, and that proton, those complicated interaction really responsible for the 90% of the proton mass, right? So this is very different from our normal experience. Okay, the mass, actually matter particle, those 3 quarks only contribute 1%. 99% from those complicated interactions, which you don't understand fully these days. Okay, and that's why this question, how does the mass of the proton arise from the fundamental quarks and gluons? It's not fully understood. So that's why we want to perform the image of those protons and study the dynamics of the strong force. The first one of the experimental major contribution along these directions is called HERA. Okay, HERA is an experimental facilities down in Hamburg in Germany. Okay. They performed experiments back in 1992 up to 2007. Okay. So this, if you look at this circumference of the this colliding ring, it's something around 6.3 kilometers. 6.3 kilometers. Now 25 meters below the suburbs of Hamburg. Okay. They colliding electron and protons. So from these experiments, you will be able to map out some images or the distributions of quarks and gluons inside a proton. Shown over here on the right side, you will see there's a blob. This is really my proton, which is moving very fast at some momentum p. And if you consider each constituent, those quarks and gluons inside a proton, what I set the momentum to be x times p. In a sense, they carry some momentum fraction of the proton x. Okay. So shown over here on the left side is this figure. Okay, and this figure it's a probability of those quark and gluon distribution, probably as a function of the momentum fraction x. As you can quickly see, if you go to relatively large x region, you will have this x u quark and d quark, and they are u quark and d quark. They are very large. Okay, And then if you go to relatively small X-ray range over here on this end, you'll find that gluon contribution is very big. So what is the gluon contribution in this case? Now the gluon contribution, as you can see from over there, I multiplied by a factor of 0.05. Otherwise, I won't be able to put this gluon curve even in this figure. So in a small X region, gluon becomes much more dominant. This is what we typically call a longitudinal motion of the quarks and gluons, because longitudinal meaning is really in the direction of my parent protons. So you want to go further, right? So far, those are the most of the knowledge about this image of the proton. In general, you want you to understand how this 3D momentum, both longitudinal and also transverse momentum, how this distribution actually distributed in the momentum space. At the same time, you also want to know how each of those quarks and gluons are located inside my proton. In a sense, I wanted to know the position distribution of my quarks and gluons. I also want you to know the orbital information in a sense. Do these quarks and gluons orbit inside a proton? And then whether they carry orbital angular momentum? Because I cannot see them, right? So all those questions I wanted to ask and trying to find a way to probing them and to extract them from experimental data. These days, when we study quantum physics, there's also important quantum correlations we want to understand, such as what are the quantum correlations between the motion of those quarks and gluons and their spin of the protons. So there are many interesting questions, and when you're imaging a proton. So this give you like, so the image we're talking about, the image over here is more in a more broader sense. It's what we call a quantum image, including momentum, position, and also like a quantum correlation. Furthermore, we also, as in the same way studying black hole, we also want to study the evolution of this image. This time, we study the evolution of this image over energy. You quickly realize if you study this evolution of the image at a relatively low energy, this distribution looks like very different. It really looks like there are 3 quarks over there. As you increase the energy, and you find it out that in a quantum system, it's kind of like a bubble. You can randomly from the vacuum bubbling out like quarks, anti-quarks, and the gluons. Okay, so you see there's a lot of quarks and gluons and get increased, get created as you increase energy. Eventually, in a higher energy, you'll find it out those gluons are starting to become very dominant. So we want you to understand how this image evolves as you go through the different energies. So the machine, so far, the previous machine is called Hera, gave us a lot of insights about like longitudinal motion of quarks and gluons. The next machine, which can map out the entire images and the correlations, momentum, position space, that next QC frontier is this guy, is what we call an electron ion collider, or EIC, which is going to be built at Brookhaven National Lab. Brookhaven National Lab is a national lab facility at Long Island in New York, in the US. So currently they are hosting this facility called a relativistic higher ion collider, which is called a RIG over there. By 2031 or around that period of time, this facility will convert into a new facility called a EIC, electron ion collider, which in this case you are colliding electron or proton or electron nucleus. So this new machine, it will allow us to provide the most precise image. So what is so unique about this this machine, this EIC? EIC, this time you can have a polarized electrons. It's going to colliding with the protons or nucleus. Right? The interest is the proton can go very high energy. The proton can both be unpolarized or even can be polarized. Right? Similarly, for electrons, it can have unpolarized or repolarized. Right? So as I said, the polarization on top of the unpolarized studies, the polarization will adding additional twists as an additional tool to provide even finer structure of those images and also provide the quantum correlations which we really wanted to study. This machine has a luminosity that's way, way higher than the previous machine called Heron. It's 3 orders of magnitude higher than those. It is because it's such a strong, such a bigger luminosity, it allows us to provide a much finer image of the protons, neutrons. So to some degree, so everyone knows the CT, right? You can very easily go to hospital and then get a CT scan and then get images of a certain part of your body. It turns, if you think about it in that way, you can think about it. EIC is really the world's largest CT, okay, to provide the image of the protons and the neutrons. I go further. So what kind of image you are actually looking at? This is again, yeah, you have to look at for when a series have some ideas. This is one of those series imaginations. This is a possible image you might be able to see once this EX machine turned on. This is a conscious theoretical framework. On the left side, so this is in a momentum space, in a transverse plane. You have a Ks and Ky, means X component, Y component of your transverse momentum. And then those are density plot showing the density of your U quarks at different momentums, So in an unpolarized case, which is the left plot, the unpolarized case, you'll see in the transverse plane, it's a symmetric distribution. On the right-hand side, you polarize, you make a proton is polarized up. You will immediately find as a distortion, okay? So there's some interesting correlation happen inside those protons. So this is some serious imagination with some data input, right? Coming from some existing facilities. So in the future, we hope to understand this much better using electron ion collider. So now let's, so you might, at this point, you might ask the questions. Why do we even care about studying quarks and gluons? Right? Why? Yeah, if you're asking this question, my answer will be the following. So realize our modern life, right? Our modern life. So it's really relies on electricity. So electricity made our modern life possible. It light our city. This is Los Angeles airport, and it will make our phone calls and the smartphone and reading news. It will make our car go. So electricity is extremely important. But deep in terms of from the fundamental science point of view, fundamentals, it's really in the earlier days in the fundamental science, we managed to understand and manipulate an electron's motion such that we be able to know and generate electricity. So those are all coming from fundamental science from much, much earlier days. Doing the same thing for quarks and gluons. Imagine, or if we could study quarks and gluons in exactly the same way as we studied the electron's motion, what will happen? Remember, the electron has a very tiny mass, consider even less than 1% of the atom's mass. So the majority of the mass coming from the protons and neutrons and embedded in it's really coming from the quarks and gluons. So imagine if we were able to study quarks and gluons motion in the same way as electrons, then we would have the possibility of unlocking the remaining 99% of the potential all the matter around us, all the substance around us. Those 99 potential, remaining potential, we don't have a clue yet. So from the theoretical, from fundamental science point of view, and it will allow us to understand and describing our universe in an even more precise way. Well, the implication is unimaginable. At this point, I don't have any imagination what that could do to our society. Similar like in a way, when we understand electron motion, what would that leads to like success in our society. Okay, so I would only say the implication are unimaginable. So as we continue develop fundamental science to understand the strong force and to further explore the structural matter using this electron ion collider, I would say we have a bright future ahead to further locking down the structural matter and uncovering those significant potential from the matter. Well, with saying that, thank you. Hope you enjoyed the history of the strong force exploration of the structural matter.
Thank you very much, Zhongbo, for this really great journey through history from the very beginnings of physics understanding of the strong force to the very most modern projects that are currently in development, like the electron ion collider.
Thank you.
Thanks a lot. That was very, very interesting. We have two questions from the live chat, and there are two questions by Unhi. And the first question she asked is, you showed that in the old days people bombarded some substances with what you said is alpha particles, and they made new substances out of it. And she asked, can one create all different substances with this process? So can you make gold, for example?
I mean, you could, not, unfortunately not.
Okay,
I don't think that's possible. Yeah, you can create some of them. Yeah, but not all of them. Especially like certain particles are like, especially heavy ones, like they are unstable, so they will automatically decay. Yeah, so it's not so easy to do.
Yeah. Thanks. And the other question that he mentioned was, you showed a slide where the electron hits the proton and it breaks the proton apart, but on that slide somehow the electron is not directly hitting the proton. Somehow there is some wiggly line, and she asks, it looks like the electron is somehow unstable or something is happening to the electron. Can you tell us what's going on?
Yes.
There.
Okay, I think you are talking about that line, that curly line over here. Yeah, so this is what we call a Feynman diagram. So what really happens? So this is I probably shouldn't put it over there. So this is more on from a theoretical point of view. So what really happens is this electron, which is this white dots, white ball, interact with a proton. So by exchanging a virtual photon. So over that wiggly line is a virtual photon. So in a sense, so this is called a quantum electrodynamics. Yeah, you don't so in a sense, you don't necessarily need to really directly hit the proton in order to get reflected. So imagine, because this is electron magnetism, right? So you have two charges, let's say, you don't need to like really in contact with each other in order to get deflected or get interacted. You can like have some distance, and that in that distance was filled in the quantum by this virtual photon. So this is what it really happens.
Thank you very much. I don't see any further questions from the audience. And that brings me then to close this session. I would like to thank Zhongbo again for this really nice and interesting presentation. And I hope that our audience also was enjoying both this talk and the two other talks that we had in store for them this week. I hope you enjoyed it, and we will have more outreach material for you quite soon here from the University of Stavanger. So stay tuned and stay hungry for more physics.
Thanks a lot. Thank you.
Bye-bye.
Yeah, very nice in making this presentation. Right.